Okay. Hello, Professor. My name is Kenny Kimera. Today, I'm going to be doing lab number 7's problem number 6. And so let's get right into it. So, oops, let me tab in. In order to start off with part A, if the dimension of V is equal to n, then there exists a set of n minus 1 vectors in V that spans the vector space V. This is a false statement. This is because for a set to span a vector space V, there must be at least as many vectors within that set to match the dimensionality of said vector space. For example, if the dimension of V is going to be equal to 3, this would of course be in R3. Then there would have to be a set of n minus 1 vectors, or have to be a set of 2 vectors that are able to span R3, which is simply not true, as they would be missing one dimension. As for example, they'd only be able to have the x and a y vector, and there would be no z vector to get the third dimension. So the statement is false. For B, this statement is going to be true. If the dimension of V is equal to n, then there exists a set of n plus 1 vectors in V that span V. This will be true, of course, because, as I stated before, for a vector set to span V, there must be at least as many vectors in the set to match the dimensionality of the vector space. And the n plus 1 is still valid because it just implies that one of these vectors will become linearly dependent, which does not invalidate the fact that the set still spans vector space V. For example, I'll borrow this from before, if the dimension of a V is equal to 3, or is equal to n as well, then there will be a set of n plus 1 or 4 vectors. For example, vector I, vector j, vector k, and then vector negative k. These will be a set of 4 vectors that still spans vector space V within R3. It is just that one of these vectors is linearly dependent on the other. However, it does still span. Now, moving on to C. If the dimension of V is equal to n, then any set of n plus 1 vectors in V must be linearly dependent. This is also true, because similarly to my explanation for part B, if the dimension of, let me write this, if the dimension of V is equal to 3, then there would be a set of 4 vectors inside of V that must become linearly dependent, which can be seen with the example. Let me just rewrite it for this line of vector I, vector j, vector k, and then vector negative k. You see this set of n plus 1 vectors, 4 vectors in this case, that is linearly dependent on each other, and it must stay linearly dependent in order to stay the proper dimension, because if they were not linearly dependent, then the dimension of V would have to be different in order to not break the rules. So overall, the statement is true. So for part D, if the dimension of V is equal to n, then any set of n minus 1 vectors in V must be linearly independent. This is going to be false, because for an easy counterexample, if the dimension of V is equal to 3, then that means there would have to be a set of n minus 1 or 2 vectors. For example, let me get a bit more detailed. Example like this. We have a set of 1, 0, 0, negative 1, 0, 0, 2 vectors that are linearly dependent on each other, but still fit within the dimension 3 for the vector space V. But they are linearly dependent, thus proving that they must be linearly dependent false, meaning that the statement overall for D is of course going to be false. Thank you. Have a good day.